Hello everyone, I'm happy to show our work TraSS to you. It is an efficient framework for trajectory similarity research based on query data store. I'm Hua Junhe, a PhD student at Southwest Georgia University. My co-authors are Associate Professor Yuan Li from Chongqing University, Zijie Ruan, Tianfu He, and Jie Bao from Jingdong Intelligent Cities Research, Professor Tianrui Li and Yu Zheng from Southwest Georgia University. Today, I will introduce our work from 6 parts to you. Trajectory similarity search is a fundamental query for trajectory data management. It searches all trajectories that are similar to a given trajectory. Trajectory similarity search is beneficial for many applications, such as companion detection, carpooling, trajectory clustering. For example, the companions often hang out together, so they usually generate similar trajectories. In recent years, Internet of Things enable us to easily capture trajectories of moving objects. As a result, a large number of trajectories have been connected. For example, there are more than 1 TB trajectories are generated by over 16,000 covers of Jingdong each day. Typically, massive trajectory data can be managed by distributed system, meaning is setting the work use Spark to support trajectory analysis. However, Spark is a memory-based framework, which consumes much memory. Besides, Spark is mainly used for offline analysis. So, Spark-based systems are hard to support update. K-value data store use a form of K-value pairs to store and query data, which is very friendly to frequent update service. The data is featured by a unicorn queen or a number of unicorn queens to retrieve the value. However, K-value data store do not natively support trajectories, so 2 core operations are required. Firstly, we should give each trajectory an appropriate key that can represent the multidimensional characteristics of a trajectory. In setting works, use the MBR of trajectory to represent their spatial shapes. Then, use a spatial index to allocate index space to the MBRs. Each index space can be completely covers the MBR of the inner trajectories and can be encoded as a key for story and query. When querying, given a query trajectory, we first generate a candidate index space based on the spatial index, and we call this step global pooling. Then we extracted the trajectories then indexed by the index space. Then in each data ranging, extracted trajectories must be checked by the strategies of local filtering to evaluate their similarities to the query trajectory. However, trajectory have irregular shapes, and similar trajectory usually have similar shapes. Thus, how to index and encode irregular shape of trajectories is challenging. When query, there are 2 core operations, global pooling and local filtering. How the global pooling can pool invariant index space, as many as possible, and how the local filtering can correctly filter dissimilar trajectory as the challenges of query precision. Code tree is a commonly used spatial index for trajectories. It basically divides the entire space into 4 subspaces. Then, a trajectory is indexed by the smallest subspace that covers it. For example, subspace of 0 and 3 are used to index trajectories T1 and T2, T and T3. However, the smallest subspace may be too coarse for a trajectory. For example, the smallest subspace for T4 is a root node that is too big for T4. Thus, exit ordering is proposed, demonstrated by our previous works. Exit ordering is the state-of-the-art spatial index for managing trajectory in K-value data stores. Exit ordering proposes a concept of a united element. It can be regarded as an intention of a code tree by doubling the radius and height of each subspace, as indicated by the arrow in the figures. For example, the united element of 0003, 303. Therefore, we can use the smallest index space to represent a trajectory. However, the united element only represents the MBR of a trajectory. That cannot reflect the irregular shape of a trajectory. For example, trajectory T1 and T2 have different shapes, but they are indexed by the same united element. Given a query trajectory, the global pooling of many existing works keeps all index space that intersect with the query trajectory. However, it may cause a large number of false hits. For example, trajectories of united element 00303 cannot be similar to Q because they are far away from Q. Then, the local filtering calculates the similarity of each instructed trajectory. However, the similarities measure usually have a high complexity because all points of two trajectories must be compared. To address shortcomings above, we propose TraSS, an efficient framework for trajectory similarity search on Q-value data stores. For representation, we propose exit star index to represent as many similar trajectories as possible within the same index. And then we use Douglas algorithm to simplify trajectories. As shown in the picture, exit star index divides each united element into 4 subquarters, then use a combination of subquarters as an index space. We give each combination a position code that represents the shape of a trajectory. As shown in the picture, T1 and T2 are located in the same united element, but they can be differentiated by their position codes. After indexing, we propose an encoding that can encode the united element and position code, such that we can efficiently store and query trajectory by the converted values. Additionally, we use Douglas algorithm to select representative points and big box, such that we can simplify a trajectory. For example, as shown in the picture, we use only 4 points and 3 big boxes to represent a 200 points trajectory. When querying, our global pooling only reset a few index space that are similar to a query trajectory. For example, only united element 03 and position code 7 can be candidate index space. Our local filtering finds this similar trajectory in a way of low complexity. For example, we use 4 representative points and 4 points to represent 200 points key. Thus, the complexity is null. This is an overview of our framework. Its core operations are representation and qualification. We propose exit star index that provides an index space with an irregular shape to represent a trajectory. We renumber each index space with a unicorn intelligence for conveniently query and story trajectory. Based on Douglas algorithm, we calculate DP features. Then we story trajectory. We provide efficient query precision to find similar trajectory from database. As shown in the picture, given a query trajectory, we first use the global pooling to fill out in this space that are impossible to contain trajectories similar to the query trajectory. Then we eliminate trajectory that could not be the final answer in the remaining index space through the local filtering on each data region. Then we will give more detail of representation and query precision. In this paper, we support featured DW and Hausdorff, and the default similarity function is featured. And we support similarity search and top case similarity search. In this part, we introduce the representation, and that's including how to calculate a united element and how to design the processing code. And our processing code can help global pooling. As shown in the picture, there are 10 processing code that can be generated by a united element. Assuming that the code 3 is far away from Q, then we do not need to extract a trajectory indexed by processing code 2, 4, 5, 6, 8, 9, such that we can reduce I overhead by 13%. We reduce I overhead by 83.6%. Irradiated data stores need a one-dimensional key to story and query data. That we diverse a bijunction function to map index space into integers. The longer the same prefix of two index space, the closer the converted numbers. Thus, the encoding must guarantee that the interval between the converting value of two index space can exactly accommodate all index space between them. Thus, we use the deep first strategy to design our encoding. This begins at the root node and numbers index space in the deep first rating order. The advantage of our encoding are the index space of a trajectory can be calculated by the mathematical formula without maintaining the instructions in the memory. The storage overhead is less than the string encode. The number of key range is less than simple concatenation. The computational of similarity is expensive because at least all points of two trajectories must be visited. However, consecutive points may be very close to each other. Thus, we use Douglas algorithm to reduce the size of trajectory without affecting the accuracy. For example, we use 4 representative points and 3 representative baby boxes to represent a 200 points trajectory. Finally, we can use an irregular shape to represent a trajectory. Then we use the index value as the spatial key for story and query trajectory. We also store the DP feature, which is beneficial to the local filtering. Then we describe two pooling structures. Global pooling aims pool irrelevant index space. Our index space is represented by an init element and position code. Thus, we first select a candidate init element. We field a position code in each remaining init element. Similar trajectory usually have similar size, so that we only extract trajectory indexed by the similar index space. Then, we pull in init element by their distance to the query trajectory. The init element is still too large to represent a trajectory. Thus, we use position code. Each index space is a compilation of 4 subcodes. Thus, we can filter irrelevant index space that contain subcode whose distance are big to the query trajectory. After filtering unnecessary index space by the global pooling, and then we extract the trajectory indexed by the remaining index space in each data range of the database. The local filtering helps to eliminate dissimilar trajectory in each range with minimal computational cost. We use the representative points and representative building blocks of trajectories to fast filter dissimilar trajectories. For more details of pulley structures and corresponding pools, please refer to our paper. Based on the global pooling and local filtering, we implement 2 queries. For similarity search, we search from the root of exit star index and filter irrelevant index space by the global filtering, then execute local filtering for each extracted trajectory. For the top key similarity, we use the best phased logarithm and 2 priority queries to find a similar trajectory from near to far. We implement TraSS based on HBase and conduct evaluation on a cluster of 5 nodes. We use 2 real datasets to evaluate the efficiency of TraSS, and we compare with reports, just data and DFT. From the result of examined, we can see that our work TraSS outperform our solutions. Additionally, we conducted examined to evaluate the effect of exit star index. Especially, we can reduce the overhead on a case and can reduce the I/O overhead. To sum up, the contribution of this paper are threefold. We propose a lower spatial index, exit star. It represents a trajectory using fine ground index space, and we support featured DTW and Hotstop, and we developed 2 efficient query precision algorithms to execute similarity search. We create an open source by integrating our framework into HBase. Our framework including support spatial range based on exit star index and support more trajectory similarity search. That's all. Thank you.